Okay, so we are doing Chapter 3, Section 3, and I realize you're looking at a slide that says 2.8, and we have already done graphing linear inequalities. However, we need to remember what we did in 2.8. We need to be mindful of the inequality that is in both of our lines for our system of equations, and decide whether we have a dotted or solid boundary. We will be testing a point to determine which side of the line for each line we will be shading. So you can test a point to be absolutely sure and make certain. If you are in slope-intercept form, you can take a look at your inequality, compare it to your y-intercept, and say whether you're going above or below that y-intercept. Since this says greater than, we can look at -2 and say this is greater than. I can go above -2 because those numbers are greater than -2. So keep this in mind of what we did when we graphed linear inequalities. In a system, we have more than one linear inequality. So here we are in 3.3. In a system, we have more than one line. So here are possibilities. When we have a solution, the shaded area, the shaded region, is our solution to a system of linear inequalities. So the overlapping shading for each of our lines is what we are interested in. You will see as we graph, there is more shading here for this dotted boundary, which is the y is -x plus 2. Here's that y-intercept and a slope of -1, and it is, of course, dotted. Here is the y is greater than or equal to 2x minus 3. Here's the -3, and it's rising at 2. It has a solid boundary. This is greater than the -3. This is less than the positive 2. So there's more shading going on for both of these lines. However, where they overlap and come together, this is the region that is the solution. And you'll see that on the practice problem we're going to do here on the video. When you get a graph that has parallel lines, you have the possibility, it is not every single time you graph parallel lines, but there is the possibility of getting no solution if there is no overlapping shading. For this parallel line, which is at the y-intercept of +1, the shading occurred for this line above the y-intercept of 1. The shading for the other parallel line that had the y-intercept of -2 went below. So therefore, their shading did not overlap, so that there was a common region of solutions. So there's no solution, because for a system of linear inequalities, it is the shaded region where they overlap, where they share solution points, because there's all these points, infinite amount of points where they share those solutions. That is the solution set, the solution points, the many solution points for a system of linear inequalities. So let's do a problem, see what we get. So we've got these two linear inequalities. I have one that's in slope-intercept form, so let's graph that. I can begin with my y-intercept at -1 and use my slope of 2 over 1 in both directions. Rise 2, go to the right one. I can rise -2 and go left 1. So here's my line. For the 3x plus y less than or equal to 4, I could change that to slope-intercept form. You're perfectly at liberty to do that. I could also do my x and y intercepts. So, and I have these backwards if that bothers you. Plugging in the 0 to find your x-intercept, 0 for y, because that's on the x-axis. You get x of 1.3. And for your y-intercept, plugging in 0 for y. For x, you get y equals 4. So that line looks like this. So here's my y-intercept at 3. Here's my x-intercept at 1.3. And so here they intersect, which is sort of nice, at 1, 1. Now let's see how we shade. So for my first one, let's compare to my y-intercept at -1. It says greater than or equal to. Well, all the numbers greater than or equal to -1 would be above that. So I will shade above this -1. So that would be all on this side of that graph. So all here, all here, all here. So and then we'll be shading over on this side of the line. Okay? So how do I shade for the other side? I'd like to test a point for this standard form line. So if I test 0, 0, this point, I put in 0, 0, 3 times 0, plus 0, less than or equal to 4. Anything times 0 is 0, plus 0, so I have 0 here. 0 less than or equal to 4, well, that is a true statement. 0 is less than 4. Remember, this is or equal to. I don't need 0 to equal 4. I need it to be less than or equal to 4. It is true. So if this is true for this line, the 3x plus y is less than or equal to 4, that means I will be shading where 0, 0, that test point is. I'll be shading to that side of that line. So it will be all towards this area, okay, to this side of the line. Now, that seems to overlap with the other line, y is greater than or equal to 2x minus 1. So I have shading going here with this line, and I have shading going here where my 3x plus y is less than or equal to 4. Well, do I have more shading over here from the 3x plus y is less than or equal to 4? No, it's over this way, towards the left-hand portion of your coordinate plane. So I don't have any overlapping. I just have shading for this one line here. Do I have any shading that's happening in this region over here towards the right? No. Do I have anything overlapping? I do have shading down here towards the bottom, below what looks like an X. I have shading, but do I have it overlapping? No, I don't, because the 2x minus 1 is shading above that line, and it does not overlap with the 3x plus y less than or equal to 4. So what I'm interested in is right here where the shading overlaps together. So here's what the shading looks like when it comes together. And that's the overlapping shading. So this portion right here where the shading comes together, this is the solution to your system of linear inequalities. And so that is what you are looking for. So very carefully see where your shading overlaps. I like my directional arrows. Shade where your overlapping is. Whoops. And that is your solution.